All right, so page 7, I'm looking at differentiability. That concept means where is a function differentiable? So basically, does the derivative exist? Derivatives exist basically everywhere in a function except at these 4 possibilities. So I say derivatives, and remember derivative means slope essentially. The derivative is the function that represents slope at a point. So like if I'm looking at absolute value of x, there is the derivative exists all along all these values, everywhere, except at 0. I've already discussed this one, if you remember from last week. I said the slopes were different on each side. That's why the derivative does not exist. Any 2 lines that meet and they're not the same slope on each side, we call that a corner. So basically any absolute value, there's going to be one x coordinate, one point where the derivative does not exist. We call that the corner. If you have a similar thing, but it's curved, it could be both sides are curved or just one side is curved. The derivative does not exist. Same reason. The slopes on each side are different. We call that a cusp. So if you have like this on one side, that's supposed to be a straight line, and a curve on the other side. Do you know what? I actually looked this up. I remember last year, because I was like, wait, which one is it? And I saw differing viewpoints. I think the right answer is cusp, but if you call it said corner, I wouldn't penalize you for that. So like some textbooks probably have it one way, some have it the other. Those go together. There's 2 others. Vertical tangent. So this one was x to the 2/3. But the function we don't see too much, but that's an example of what that looks like. This one we know, cube root of x. Square root of x would have been this. But cube root of x goes down like this. Now right here at 0, the slope is completely vertical. You can't, the slope is vertical, it's undefined. So if you had a slope that's undefined, you can't have a derivative there. The derivative is slope. All right, so right there, I don't want to draw this in because it looks like an asymptote. It's not. It's just right there, the slope of m is equals undefined. The last case is the most common and the one we look for the most. The others will come up, yes, but this is the most common. If it's not continuous, it can't be differentiable. Discontinuity. There are many. This is just a step function. There's a whole right all along here. Okay, but the most common, is there a break in the graph? Well, it can't be differentiable because you need to have a slope exist. Same as this one, like the slope doesn't exist if it's not continuous there. Those are the 4 types. Any thoughts on those 4? So actually what I want to do is, don't turn the page yet, but on the next page I want to do, why don't we do that now? You know what, I didn't do this earlier. No. Let's wait for a second. I want to do 3 examples of this on the next page. And the main question from this section is really just, is a function differentiable at a point? And you look for one of these 4. Okay, so I want to show you a couple other things. One is something with your calculator. The first one is this, though. It's something called local linearity. I want to show you x squared and absolute value of x. So I'm going to go to Desmos. Okay, there's x squared and absolute value of x. And here, I want you to watch what happens as I zoom in at 0, because we know 0 is the probable one for absolute value. So I'm going to zoom in at x equals 0, and we can see what happens. Okay, do you see how absolute value has almost essentially not changed? Right, absolute value still looks like a v, but even if we zoomed in a lot, it still is a v. However, x squared now looks like a line. Right, it looks like a straight horizontal line. This is a concept of local, being close up, zoomed in. Local linear, line, local linearity. if you can, hopefully I say it here, a function at a point will look linear if you zoom in enough. That means the derivative would exist. If it doesn't look like a line when you zoom in, where's my Desmos? Back here. If it doesn't look like a line when you zoom in, then at that point it's not differentiable. So x squared ended up looking like a line, right? So that one's fine. It's differentiable. Absolute value x is not 0. So you can actually do that for any function, guys. If you zoom in enough, it's most functions, like just x cubed or something else. If you want to zoom in at a point, it's going to look like a line. Abby, you want to close the door for me real quick? It looks like an x cubed. And let's just go up here, like x equals 2. Right here. Thank you. Okay, well, we can already see, isn't it looking like it doesn't have to be a horizontal line, by the way. Doesn't it at x equals 2, it's right here. Looks like a line, right? Absolute value continued to look like a V. So that's local linearity. So that's just a tool. I'm not going to ask you much of a question on that, but that could help you if you're wondering at a point, is my function differentiable? Any thoughts on that one? Okay, calculator time. Your calculator these days, they're so advanced, they can do a derivative. They can get you the slope, the derivative at a point. So I am just going to ask you on a quiz or test just to be able to do this in your calculator. It can also be if I ask you to find the derivative and get the slope, you could use this as a way to check. Because I probably still want you to show your work, but this is a good way to check. All right, so I'm going to show you 2 ways because most of you will have 2 calculators, either the Inspire or the 84. So the first I'm going to show on the 84. Oops. Okay, so on the 84 it's pretty simple, math 8. You hit math. Number 8 is in deriv, meaning numerical derivative. So you hit 8, you'll get something that looks like we saw with the notation. Remember there's like a d, dx type notation thing. This one's the variable. So you're going to put in the variable. Let's hit the variable button. Oh, that didn't work. I'm going to hit the variable button. X. The next one says, what function is it? So you know what? Let's just do something random. Let's do 4x squared. I mean, you can do whatever you want here. Minus 3. It's parabola. Move down 3. And then it's going to say x equals, and that's the point. What point do you want? What x coordinate do you want? You want to do 2? At 2, what do you want this? Calculate to find the slope at what point? At 2. X equals 2. You hit enter. It gives you the slope at that point of 6. As simple as that. Math 8. You hit the variable, you hit your function, x equals whatever you want. Make sure to bring a calculator if you don't have yours. Graphing calculator, yeah. Now, Inspire. So if you have the, let's see, here it is. Let's see, clear, get rid of that. Well, oh, that's right, okay. So if you have the Inspire, you have to go to the calculate screen. So there's like a graph. There's, if I go home, you know, there's graph and there's calculate. So I'm going to go to calculate. I'm just going to hit B. So it takes me to, that was the wrong one. I need to go to A. Or you get an arrow there. You go to calculate and you hit menu. So basically that's the difference. Instead of math 8, you hit menu. And you'll see calculus, and you'll say, hey, I'm going to hit that one. Sure. So it's number 4. And then numerical derivative at a point is the first one. This one's a little different on here. You do the variable, yes, x. Then you hit the value, we did 2, at x equals 2. You hit OK, and then it gives you basically the setup as before. So I think it's a little different, the layout there, but it's still 4x squared. Did I have minus 3? Minus 3. And then it spits out 16. All right, so derivative at a point to get you that slope. If you're still not getting it, I'll be around in a minute. But got it good so far? Anybody need general help? Okay. Well, let me know in a few minutes if you still need help with that. Okay, and then moving along, so here's something, I've actually already talked about it with continuity, but it is important. It says differentiability implies continuity, but continuity does not imply differentiability. So let me explain the first part. If a function is, this correlates with this one. If a function is differentiable, it's continuous. So like x squared, if you can do the derivative like we did at any point, then it's mandatory that it had to be continuous. Like, if it's not continuous, you wouldn't be able to do a derivative. So if you can do a derivative, yeah, it automatically was continuous there. The second part says the reverse is not true. If a function is continuous, it's not necessarily differentiable. And the classic example is absolute value of x. A function is continuous, but at 0, at x equals 0, it is not differentiable. We already talked about that. The slopes are different on each side. So a graphical quick example here. Not differentiable in this little graph at A because it's discontinuous. There's a hole. By the way, it could be a hole or an asymptote. Both are discontinuities. At B here, not continuous because it's a corner, or actually it looks curved, so it could be a constant. We'll be fine with that. Here's a vertical tangent, so it's continuous, it's differentiable everywhere else on here except these. At C, it's not, there's vertical tangent, and really this one need to be connected more. So here's a little tool for what you do with these, because here's the question. It's going to say, here's a function. Is it differentiable everywhere? Where is it not differentiable? First, see, is it continuous everywhere? If it is, then move on and think about the slopes. Are there corners or cusps? So first check continuity. Okay. If the continuity is good, move on to 2. Check the slopes. Derivatives. Subtract the slopes on each side. Turn the page. We're going to do these 3 to finish up. So here's the overall question for this section. Here's a function A. Find the values, the x coordinates, where it is not differentiable. Because it's kind of assumed it's differentiable everywhere except at certain places. You can put one of these 4 as the reason, and then if the function is differentiable everywhere, write none. So there was no problem with it. It's kind of like when we did continuity with these. Remember where we kind of the same thing, we checked continuity. If it was continuous, we wrote none. Like no breaks in the graph. Okay, so let's look at A. I see a cube root of something plus 5. Now, the basic parent function for cube root was this. Right? Cube root of x looks like that. Just from that knowledge on the last page, that was the basic one right here. There at 0, remember there was a slope that is actually vertical. So the slope is undefined. Well, this one is just some sort of transformation of that, right? So there will be another vertical tangent. If you remember from transformation, the inside is really going to transfer right and left, and the outside moves it up 5. Also on this, if you needed a graphing calculator, to help you with this, that's fine. Basically, the inside is going to tell me what it's moving. And since it's minus, it's moving right. Okay. Well, if I factor out a 3, it would be x minus 2. Factor out a 3, be x minus 2. Therefore, right here, that tells me it's moved right 2. It's also moved up 5. So this would have to be 5 up here. It's also moved up 5, but that doesn't affect the x coordinate for the vertical tangent. It's at x equals 2. It says name the type, it's a vertical tangent. Again, if you didn't know graphing calculator, you could use it here. The other thing you could do is just set 3x minus 6 equal to 0. And that would give you the x coordinate of 2 as well. Okay, so that was one you got to think. Some of these are just think about the function. Bless you. Think about the function. What does it look like? That kind of thing. All right, let's look at B and C. Very similar. They're piecewise. First, x squared, 2x minus 5. Those are both continuous everywhere. Right? Parabola and line. Continuous everywhere. Same, a line and a parabola both have a derivative everywhere. Right? That one's fine. A line has a slope everywhere. No problems, no breaks in the graph. The only question is at 1. Remember what it is with continuity? It's the same type. Like the main question is usually, all right, at where it connects. Is it even continuous? This is what I was talking about back here. First, you have to see, is it even continuous? If it is, then you got to check the slopes. All right, so let's do this one. Check continuity. It's very simple. You plug in the x coordinate of 1. Trying to see what is the y coordinate doing when x is 1. Well, the top one I get 1. 1 squared is 1. 2 minus 5, here I get negative 3. They're not even continuous. So like parabola and lines like this. I just made those up. It's that 1 here. But that's what it is, not continuous. Therefore, I'm going to write, okay, find the values where it's not differentiable at x equals 1. There's a break in the graph. So there's a break in the graph, so I put discontinuity. It's a jump. Okay, and the last one, same setup, right? But I changed it slightly to 2x minus 1. So let's check 1 again. These are x squared, 2x minus 1, continuous and differentiable everywhere. Well, let's check at x equals 1. Well, at x equals 1, when I plug in 1, 1 squared is 1. Down here, 2 times 1 is 2, minus 1 is 1. So it's continuous. Basically, it looks like here's 1. It's just the line takes over with, that was bad. It's going like this. The line takes over with the same slope. It's like parabola, and then the line just, same slope right there, continues on. Just rewrote that. So that's good. It is continuous, but it could still be like this. Or it could be a parabola, it could be like that. Parabola being the line, where the slopes are not the same, right? So let's check it out and see. Let's check the slopes. I'm going to start with the bottom one. What's the slope for that one everywhere? It's 2. It's right. It's still the line is the m value right there. For x squared, to find the slope, if I said you could do it on your calculator, you could put it in. What I just taught you, right? Calculator, math 8. If I said you had to do it by hand, then you had to do the limit definition. So depending on what I say, calculator maybe, if not, limit definition. So either one. Okay, so calculator, it's going to give you the same number. I'll do it by hand real quick. I'll just show you what I would do. I would, you know what? Let's leave it as a plus h. A squared. It was just x squared, right? just, okay, it's just x squared. So when I put a plus h, I'm going to use this, a plus h in there, it's that, minus when I put an a, it's this. This one, when I FOIL, will become this. I'm skipping a step or two, I know. The a squareds cancel. And then I can factor out an h from the numerator. And the h's cancel. We've done this one a few times, that's why I'm just going through it. I put in 0 for h, and I get 2a. We've seen that one actually as well. X squared getting the 2a. So then what I do, so let me go back here. So then this was, the function, the derivative was 2a. So then I put in 1 to get the slope. I put in 1 for a, 2 times 1 is 2. So what happens is that this is continuous, the slopes are the same. The answer is done. It was fine. It was continuous, the slope for the parabola where they met and the line were the same. If you'd gotten any other number, you put corner or cusp, because it would look like this. Where the slope there and the slope there are different. That's all I got for today. Any